All right, next one. I have a little bit different of a definition from the book. Two events are independent if and only if the probability of A intersect B, where A and B are my two events, is equal to probability of A times probability of B. And I should have probably put up here that the two events are A, comma, B inside a sample space. The type of definition, this is a property of two events, so it's a property. So let me show you an example. If I have two die and I let S be the set of ordered pairs ij, where I and j run from 1 to 6. So I think Colonel Watts actually talked to you about thinking about the sample space carefully, that sometimes it's an ordered pair. And let's suppose that each point was assigned to the probability 1 over 36. So I have a 1 over 36 chance of getting each point in this 36 size sample space. So let A be the event that A is the first die rolls a 1, 2, or 3. Not or 3, but it's or 3. And B be the event that the first die is 3, 4, or 5. Well, A is a subset of S, and it looks like this. I just listed it all out so I could see it. I'm not going to list B out. You can imagine what it is. A intersect B, on the other hand, is just this last row, because B is the only one they share is 3. And so in A intersect B, I have six guys in here. There's 36 in the whole sample space. If I reduce that, I get 1/6. On the other hand, the probability of A is, I have 18 ways that can happen out of 36. It's a half. And the probability of B is a half. And it turns out that probability of A times probability of B is 1/4, which is not 1/6. So it's not independent. So this is the definition of independent. So if I had you in class, I would ask you, what do you think independent is? And you would sit there for a while and maybe say things of what you intuitively think it is. This is the raw definition, mathematical definition of what it means to be independent. So why do we care about these kind of definitions? Well, if I have things that are, if I take just everyone with lung cancer and, I have other examples, but this is an example that was given in Robert Ash's book, where people have lung cancer, and then I look at the people who smoked. You would think that these are not independent events. So you would think that the probability that the probability of the A happening where given B is going to be higher than if I just looked out into the regular population and looked at everyone. So we write the probability, the conditional probability of B given A, it's given by this formula, probability of A intersect B divided by probability of A. And here in the definition, the probability of A has to be greater than 0. If you look in your book, they've left this out. But of course, this won't make sense if the probability of A is equal to 0. Definitions need to be tight. All right, I'm going to show you an example. This came from Robert Ash's book. If I have two unbiased dice and I throw them, die, I guess, would be not dice. And A is that the event that the sum of the faces are 8, and B is the sum of that the faces are equal. Well, A looks like this set up here, and B looks like this set down here. So probability of B given A, if I run through the formula, is probability of A intersect B divided by probability of A. A intersect B has only one thing in it, so the probability of A intersect B is 1 over 36. The probability of A, I have 1, 2, 3, 4, 5 things in it. It's 5 out of 36. So the probability of B given A is 1/5. By the way, in your definition in your book, when they gave independent, they also had that probability of B given A is equal to the probability of B. Or backwards. They said the probability of A given B is equal to probability A if and only if A and B are independent. They added that. I didn't need it because now I can prove it. So the probability of A given B, running through the formula, is given by this from conditional probability. Now, if A and B are independent, then this is true. And that came from Robert Ashe. I can cancel it, and I'm given probability of A. So this part is a consequence of probability of A intersect B being probability of A times probability of B. You don't need to include it in the definition. And it's if and only if, and this is if and only if. If and only if you remember from, I guess, only one person or two people took foundations, but it means you have two proofs. You have to go this way and prove it, but you can just string them along the back way, and probability of A is this and this and this. So these two things being equal is a direct consequence of these definitions. It's not part of the definition. So the law of total probability, I'm going to pause on that one and upload this video.